Welcome to the 14th lecture in abstract algebra. The topics that we'll explore in this lecture include the cross product of three-dimensional vectors, and we will revisit the quaternions, this time as a real vector space.
Okay, so we'll start with the definition of the cross product. Let the set V be a three-dimensional vector space over the field F, and let U and V be two such vectors. The cross product of the vectors U and V, which is denoted U cross V, is given by the ith component of U cross V is epsilon sub I j k U sub j times V sub k. That is, the ith component of the cross product is the sum of the products of the components U sub j times V sub k for a fixed value of the index I, and the indices j and k are permuted. That is, the cross product U cross V is the three-dimensional vector whose first component is epsilon sub 1 jk U sub j times V sub k. And so the indices j and k can have the values 2 or 3. The second component is epsilon sub 2 jk U sub j times V sub k, where the indices j and k can have the values 1 or 3. And the third component is epsilon sub 3 jk U sub j times V sub k, where the indices j and k can have the values 1 or 2. So notice that the cross product is specifically defined on three-dimensional vectors. Later we will look at a generalized notion of vector multiplication that is not restricted to 3 dimensions. But for now, let's begin to look at the algebraic properties of the cross product. So as a lemma, we will show that the cross product is anti-commutative. That is, the product U cross V is the additive inverse of the product V cross U. So proof. Once again, the ith component of U cross V is epsilon sub I j k U sub j times V sub k. Now the components U sub j and V sub k are scalars, and so they commute, and so we have epsilon sub I j k V sub k times U sub j, and this is the negative of epsilon sub I k j V sub k U sub j, and this is the negative of the ith component of V cross U. And so the ith component of V cross U is the negative of the corresponding component of U cross V. And so indeed, U cross V is the negative of V cross U. So next, as a lemma, we will show that the cross product is not associative. So proof. we will compute the first component of the cross product of U with the cross product of V cross W. And so this is epsilon sub 1 jk U sub j times the kth component of V cross W and so with the fixed value of 1, the permutations are 1, 2, 3 and 1, 3, 2, the first of which is even and the second is odd, and so we have epsilon 1, 2, 3 U sub 2 times the third component of V cross W plus epsilon sub 1, 3, 2 times the, U sub 3 times the second component of V cross W. So now evaluating the permutation symbols, we have U sub 2 times the third component of V cross W minus U sub 3 times the second component of V cross W and so we have U sub 2 times epsilon sub epsilon sub 3 jk V sub j times W sub k minus U sub 3 times epsilon sub 2 jk V sub j times W sub k. So with the fixed value of 3, the permutations are 3, 1, 2, which is even, and 3, 2, 1, which is odd. And so we have U sub 2 times the difference, U sub 1 times, V sub 1 times W sub 2 minus V sub 2 times W sub 1 minus U sub 3 times the quantity. And here, with a fixed value of 2, the permutations are 2, 3, 1, which is even, and 2, 1, 3, which is odd. And so we have U sub 3 times the difference, V sub 3, W sub 1 minus V sub 1, W sub 3. And so we have U sub 2 times V sub 1 times W sub 2 minus U sub 2 times V sub 2 times W sub 1 minus U sub 3 times V sub 3 times W sub 1 plus U sub 3 times V sub 1 times W sub 3. So I'll rewrite this. So the first component of the cross product of the vector u with the cross product of v cross w is u sub 2 times v sub 1 times w sub 2 plus u sub 3 times v sub 1 times w sub 3 minus the quantity u sub 2 times v sub 2 times w sub 1 plus u sub 3 times v sub 3 times w sub 1. So next we'll compute the first component of the cross product of u cross v with w. So this is epsilon sub 1 jk. The jth component of u cross v times the kth component of the vector w. And so we have epsilon sub 1, 2, 3 times, or rather the second component of the vector u cross v times the third component of w plus epsilon sub 1, 3, 2, the third component of u cross v times the second component of the vector w. So again, evaluating the permutation symbols, we have the second component of u cross v times the third component of w minus the third component of u cross v times the second component of the vector w. And so this is the third component of the vector w times epsilon sub 2jk u sub j times v sub k minus w sub 2 times epsilon sub 3jk u sub j times v sub k. And so this is w sub 3, and we're going to combine a few steps here. The permutations with a fixed value 2 are 2, 1, 3, which is odd, and 2, 3, 1, which is even. And so we have u sub 3 v sub 1 minus u sub 1 v sub 3 minus w sub 2 times the difference, where with a fixed value of 3, the permutations are 3, 1, 2, which is even, and 3, 2, 1, which is odd. And so we have u sub 1 v sub 2 minus u sub 2 times v sub 1. And so we have u sub 3 times v sub 1 times w sub 3 plus u sub 2 times v sub 1 times w sub 2 minus the quantity u sub 1 times v sub 3 times w sub 3 plus u sub 1 times v sub 2 times w sub 2. So comparing this with the first component of the cross product of u with the quantity v cross w, we see that the difference is in the quantity that is being subtracted. And so in general, the first components are not equal. So the first component of u cross the quantity, v cross w, is not the same as the first component of the quantity, u cross v cross w. So as they differ in at least one component, we have that the product, the cross product of u with the cross product of v cross w, is not equal to the quantity u cross v cross w. Okay, so next we'll look at a geometric property of the cross product. The vector u cross v is orthogonal to both vectors u and v. So proof. We'll compute the dot product. So the dot product of u cross v with the vector u is the same as u dot u cross v. And this is the sum of the product of corresponding components. And so this is u sub I times the ith component of u cross v, which is u sub I times epsilon sub I j k, u sub j times v sub k. The factor u sub I can be brought inside of the sum so that we have epsilon sub I j k, u sub I, u sub j times v sub k. So notice that the indices I and j can be permuted so that we can collect these in pairs of even and odd permutations. So let's calculate this sum. And so we have epsilon sub I j k u sub I u sub j times v sub k is epsilon sub 1, 2, 3, which is even, u sub 1, u sub 2 times v sub 3 plus epsilon sub 2, 1, 3, which is odd, u sub 2, u sub 1 times v sub 3 plus epsilon sub 2, 3, 1, which is even, u sub 2, u sub 3 times v sub 1 plus epsilon sub 3, 2, 1, which is odd, u sub 3 times u sub 2 times v sub 1 plus epsilon sub 3, 1, 2, which is even, u sub 3 times u sub 1 times v sub 2 plus epsilon sub 1, 3, 2, which is odd, u sub 1 times u sub 3 times v sub 2. So notice that we have put them in pairs so that the two permutations are opposite, and we have, because of the commutativity of scalars, we're going to have pairs that are in same product but opposite sign. That is epsilon sub I j k of u sub I u sub j v sub k is the sum of the quantities u sub 1 times u sub 2 times v sub 3 minus u sub 1 times u sub 2 times v sub 3 plus u sub 2 times u sub 3 times v sub 1 minus u sub 2 times u sub 3 times v sub 1 plus u sub 3 times u sub 1 times v sub 2 minus u sub 3 times u sub 1 times v sub 2, which is 0. That is, the dot product of u with u cross v is 0, and hence the vector u and u cross v are orthogonal. Similarly, we have that the dot product of u cross v with the vector v is the same as v dot u cross v. Again, this is the sum of the products of corresponding components. So we have v sub I times the ith component of u cross v, which is v sub I times epsilon sub I j k u sub j v sub k. Again, we can bring the factor v sub I inside of the sum so that we have epsilon sub I j k u sub j v sub k times v sub I. Notice that the permutation j k I is an even permutation, or rather is the same as the permutation I j k, and so we have that this is equal to epsilon sub j k I u sub j v sub k v sub I. And again, we can group these in pairs so that we can permute the indices k and j in a pair where one is even while the other is odd, and so this is 0. That is, the dot product of the vector v with u cross v is 0, and hence the vectors v and u cross v are orthogonal.